Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on inverse trigonometric functions. So this is the last unit in our trigonometry chapter. And again, what I'm going to do is work through my slides and give you basically the same lecture and notes that I gave my students. So therefore, you will have an answer key that you can kind of reflect on and hopefully learn a little bit more about inverse trigonometric functions. Hopefully that is why you are here. So basically what we're going to cover in this chapter is how to evaluate the inverse of any trigonometric functions. Even though I did change that, I don't cover the reciprocal functions. We'll do that later. I talk about how to apply and understand the restriction to the inverse trigonometric functions, how to evaluate the composition of trigonometric functions and their inverse, and how to use right angles to evaluate the inverse without using a calculator. So we are still on a non-calculator version. But to understand, these inverse functions, let's just kind of go back to what we did inverse functions with when we were just doing inverse functions with, quadratics. And if you remember when we were dealing with the quadratic function and finding its inverse, there's a couple ways, algebraically that we did this. First thing, we represented the f of x we used to use the variable y, right? And that allowed us just to do the algebraic process a little bit easier. Then we'd swap the x and the y, and then you just solve for y. Now, this was the first time that we introduced the plus or minus the square root of x, which was very, very important. So therefore, when you're graphing this, you have the positive version of the square root of x and the negative square root of the negative version, square root of x, which is basically just a reflection about the x-axis. And then you just replaced it using our inverse notation, which was f, with the -1 up top. So that was the inverse, but the problem with chapter one was on functions. And if you look at that graph, it does not pass the vertical line test. So we basically just considered then the function x squared does not have an inverse as it's written, but basically it just has an inverse that is just not a function, right? So we just said, it's not invertible. And the way that we could describe that or understand that was anytime that a function was not one-to-one, basically it does not pass the horizontal line test, then its inverse is also, the inverse is not going to be a function. So therefore we just say it's ininvertible or it is not invertible. It does not have an inverse. Another way we look at graphing rather than solving and doing that plus or minus, you could also reflect about the y equals x line. And that was usually like the preferred quicker method of being able to graph a function in its inverse. And that's exactly what I do for the rest of these examples. So since our x squared was not invertible, right? Its inverse was not a function. Basically what we did is we applied restrictions. So this is what we did in chapter one. Whenever we had a function that was not invertible, we applied restrictions. And the restrictions don't really change much when we're dealing with the inverse function. Like here I have g of x equals x squared for x values greater than 0. So the only difference here is like when I find the g inverse of x, like algebraically the process is the same. The only difference is I don't need to include the positive and the negative version because you can see when you take the inverse of that positive version of the red graph, I only have the positive version of the square root of x. So you don't really need to put the plus there. I was just putting it there just to kind of emphasize that it's the positive square root of x. But you can see that red graph passes the horizontal line test and the blue graph passes the vertical line test. So therefore, by adding the restriction, we allowed ourselves to be able to find the inverse of g of x. And the other most common restriction that we had was, we could also do x is less than 0. So now we take this parabola and we just restricted it for all x values less than 0. Again, algebraically, the work is going to be the same, but now you're going to get y inverse is now the negative version of the square root. So now you can see that the restriction here on our restriction impacts our final answer to be the negative square root of x. And you can see when I reflect that, how that is that reflection. That is the negative version of that square root of x right there. It's not both versions, right? And again, you can see that is one-to-one, and this is indeed a function. However, we didn't really play around with this, but in reality, we could really pick any restrictions that we wanted to, like at all. And so by applying our restrictions, like for instance, if I chose the restriction 1, 2, the important thing is when I do the restriction 1, 2, that limits my function to make sure it's one-to-one, right? And therefore I can find the inverse, which is again going to be positive square root of x, but it's going to be restricted from 1 to 4. But it's important. You just don't want to say, well, any restriction then is going to make a function because if you restrict it from -1 to 1, look what happens. you have a red graph that's not 1 to 1. So when you find the inverse, again, it's not going to be a function. So therefore, just adding a restriction does not make it invertible, meaning we have to be smart with our restrictions. So there's really two things I wanted to come away from this. Is one, if a function is not 1 to 1, then it is not invertible. Basically, the inverse is not going to be a function. So we have to make sure that when we are finding the inverse of a function, it has to be invertible, meaning 1 to 1. In the same respect, we're going to do that by adding restrictions, but we just can't add any restrictions. We want to be smart about those restrictions to make sure that they are going to include this or to make sure that it's going to be 1 to 1. So that's what we kind of talked about. And then we looked at Desmos, and by looking at Desmos, basically what we did is we looked at the graphs for each of these. And actually, you know what? Did I go through this? Yeah, let's go through this. Okay, so on the graphs, one of the things we looked at is, looked at the sine graph, and we say, ooh, that's not 1 to 1, right? That fails the horizontal line test miserably, right? Create any horizontal line, it's going to cross it multiple times. So the inverse, you can't even draw the function inverse would definitely not be a function. You can see that it would just be a squiggly line, right? Going vertically. So that would obviously not be a function. So what we need to do is we need to restrict the graph. And so what I had students do is let's just play around with some restrictions. Let's pretend it was only x values that were greater than 0, right? Okay, well that works. But again, remember this graph continues on and on. So that's not going to work. Because obviously you want to restrict the negative values, that's cool. But if you just keep on going positive, it's still going to fail. So then we said, well, if we look to the right, the farthest we can kind of go to the right here is going to be pi halves. Because once I go past pi halves, the graph, the y values start to repeat themselves. So let's say the farthest we want to go is pi halves. And then as we start going to the left, I can go to 0, but I can actually go all the way over to negative pi halves. But if once I go to the left of negative pi halves, the y values are going to start to repeat themselves. So what we did is we say, well, the best restriction then is going to be between negative pi halves and pi halves. And you can see if I restrict the sine graph between negative pi halves and pi halves, then that is going to make the function 1 to 1. It's still the same function. I'm just restricting it between negative pi halves and pi halves. And you can see that is now 1 to 1. And that's going to cover the most amount of y values with it remaining 1 to 1, because you can't go any farther right or farther left without the y values repeating themselves. So again, that's the function that we're going to reflect. So then we took the y equals x line, and I said, all right, that's what the graph looks like. And what do you know? You can see how this is actually programmed into Desmos, into this. And same thing with your graphing calculator. It has that restriction actually programmed in, because you could have chosen anyone. We could have done, this interval in 3 pi halves to 5 pi halves, right? Or negative 5 pi halves to negative 3 pi halves. But why use those intervals when we have negative pi halves to pi halves, right here at 0, right? So you can see here, that is how that restriction is. Now, the other thing I just wanted to point out with the students is, as far as understanding this, is we have this restriction. Remember these points, that's negative pi half to negative 1. And if you remember a function in its inverse, it's just the swapped version of those points. You can see here, that's 1, 1 comma 1 half, and this one's going to be negative 1 comma 1 half. So remember, you just swap the x and the y's. That was something that was very important. And if I can even get rid of the x, you can see how, again, that kind of works. You see how they're reciprocals of each other. All right, let's do the cosine. So the cosine, we kind of looked at the same thing, right? This goes on and on and on forever, fails the horizontal line test miserably. We could break it up into all values greater than 0, but again, that's not really helping us. So let's just say how far to the right we want to go, and let's just kind of start at 0. Well, if we go to 0, if we start at 0, we go to the right, we say the graph really doesn't start repeating, the y values don't repeat themselves until we get to pi. And we can't really go farther left, right, like we did with sine, because then the y values repeat itself. So it looks like our interval is from 0 to pi, which indeed, that is our interval, from negative 0 to pi. And you can see that that graph passes the horizontal line test. So again, using our same kind of idea, if I wanted to reflect this about the y equals x line, then I just do my cosine inverse, and you can see how that is a nice little reflection. Again, the coordinate points are swapped, right? Here's 0, 1. What do you think this one's going to be? Maybe 1, 0? This point is pi, negative 1. This one's going to be negative 1 pi, right? So you can see again how that swapped version, that y equals x, remember, swaps the x and the y axis. And also just wanted you to see how we restrict the domain. Again, this is something like you can't graph. If you were to reflect this whole graph, it would not be a function, right? So this software has it programmed that cosine, we are going to restrict cosine from 0 to pi, therefore we can find the inverse. Because if we didn't have that restriction, we would not be able to find the inverse. It wouldn't be a function, right? It'd be invertible. So that's why the restriction is very important. And so right now we have sine is from negative pi halves to pi halves, and cosine is restricted from 0 to pi when we need to find those inverses. The last one is looking at the tangent. Now, the nice thing about tangent is actually the easiest, because tangent, we don't really need to like find the interval. Like we can see that, like I could pick any one of these, right? Any one of these little S curves is 1 to 1. So then what's usually like going to be the best one? Well, I would say the one that's right by the origin, right? So all we really need to do for this one is just remember, well, how far to the left and how far to the right is that? And if you remember from the parent graph for tangent, those are going to be your vertical asymptotes, negative pi halves to pi halves. Oops, not that one. There we go. There's tangent. So you can see where that green graph is. And then if I get rid of it, now I just reflect about the y equals x line, and I get this lovely graph. Not that graph. Where's my tangent inverse? Oh, I need that graph. And then this graph. There we go. Should be a different color, but either way. So you can see again how that is reflected. So tangent, it has the same restriction as sine, negative pi halves to pi halves. And that's something that we're going to want to keep into our notes. So let's go back into the notes and look at that. So in my class, we just basically kind of talked about those restrictions, where they kind of came from, because again, we could have chosen any restrictions. And I just wanted students to understand why those restrictions made the most amount of sense, because they are adopted as the go-to restrictions that we use for our trigonometric functions. So I just kind of went through, some notes here. Here's the initial period. Again, kind of looking at those points, you can see that the x values are restricted from negative pi halves to pi halves. And then obviously my graph is not a very, it's not a very good square kind of xy axis, but I just kind of did my best to represent that reflection. And again, you can see, remember, the domain and range are also swapped, right? That's just kind of like that interesting kind of portion of understanding the inverse functions. And then the cosine, same kind of idea here. When you reflect that, you can see that was that same graph we got from Desmos. Again, the coordinate points are swapped, therefore the domain and ranges are swapped. But again, like remember, cosine has a domain of all real numbers. So you can't have, again, that's why we have to restrict it for us to be able to find that inverse. And then obviously we look at the tangent again, and just understanding those restrictions. So really the main thing is now understanding this notation for the inverse, because previously we used the notation for f inverse of x, which is really kind of like the same idea, f inverse of x. But again, so that's not raising f to a negative first power. You're not raising cosine to the negative first power. That is just our inverse notation. Also in calculus, it's more, we more often use the arc cosine, which really kind of represents the exact, it's the same thing. It's just a different version of that. So we use that more often in calculus. But in this class, I'm primarily going to just use the this -1 notation. And then I just kind of summarized again those restrictions. You can see how sine and tangent are the same. And then really the main thing is like understanding what really we're asking for, right? When I say cosine inverse of square root of 2 over 2, what I'm asking for is the cosine of what angle is square root of 2 over 2, right? Cosine inverse of square root of 2 over 2, that equals an angle. So that's really the big nugget out of these notes, is when you're trying to use cosine inverse, you're looking for the angle. That is what we are looking for. What is the angle? So we use inverse trigonometry to find the angle. Remember, sine, cosine, tangent, all the trig functions, those are ratios of side lengths, of comparing side lengths. So, but those are comparing side lengths based on an angle, right? It's the sine of something, cosine of an angle, tangent of 30 degrees or pi over 6 or whatever. But you're always doing the trig functions of an angle. And so now we're using our inverse trig functions to actually find the angle. So again, that's that main thing, is when you're using inverse functions, you're looking for the angle. In this class, our default is going to be find the angle in radians. We're not going to work on finding the degree or finding the angle in degrees. Another thing that I work on or just kind of expose the students to is, if you're using cosine inverse of square root of 2 over 2 equals theta, well, then you can actually rewrite the statement as cosine of theta equals square root of 2 over 2, right? If you can write cosine inverse of square root of 2 over 2 equals theta, then just rewrite it as cosine of theta equals square root of 2 over 2, right? Because that's what you're asking. Cosine of what equals square root of 2 over 2. And this is the same thing we did in division of polynomials. Like 12 divided by 4 is equal to 3. It's the same thing as 3 times 4 equals 12. And just remember that cosine is that inverse operation, right? We undo it with kind of cosine when you get to that solving portion. So we're going to do solving more in next chapter, but I just wanted to kind of expose students again to understand, to really drive home that cosine inverse, like what it means and why we use it. Because now we're going to evaluate some problems. So the first problem is sine inverse of 1/2. So again, I'm looking for what is the angle, the sine of what equals 1/2. Well, the problem is there's two angles, right? You can say, and I'll even write this down here, the sine of pi over 6 equals 1/2, and the sine of 5 pi over 6 equals 1/2. Now, there's actually infinite many answers, right? You could keep on going larger coterminal angles, but these two angles, at least on the unit circle, work. But the main thing is, remember, sine has to be restricted between negative pi halves and pi halves. So you can't just pick any angle. It has to be the only angle here between negative pi halves and pi halves. So instead of a lot of times writing down that function, what I will do is I'll just kind of draw this little restriction here, negative pi halves to pi halves. And you can see the angle 5 pi over 6 goes outside of the restriction. So 5 pi over 6 is not within the restriction, so therefore we can't use it as far as our inverse. The only angle that makes sine of pi over 6 equals 1/2 is going to be pi over 6, and that remains within the restriction, so that is our answer. Cosine is negative 1/2. Again, cosine is going to be negative 1/2 at 2 pi over 3 and 4 pi over 3. So we could say, cosine of 2 pi over 3 equals negative 1/2. Cosine of 4 pi over 3 equals negative 1/2, right? So those are the two angles, or at least those are at least two angles that give us negative 1/2. But again, our restrictions for tangent, actually, I'm going to write these restrictions. Negative pi halves, comma pi halves. Cosine, inverse cosine, remember we restricted that from 0 to pi. So the only angle that I have up here that's between 0 and pi, a lot of times it's just easier to draw that kind of like red ring, is you can see 2 pi over 3. 4 pi over 3 is outside the restriction. So therefore, we're only going to have 2 pi over 3. And again, the other thing I mentioned to the students is, remember, these are inverse functions, right? There's only one answer. So even though I'm graphing using the unit circle, I'm giving you two options, there's only one answer that meets the restrictions of cosine. There's infinite many answers. And actually, this is a really important point that I probably should go up to there. I'll drive this kind of home like, let's do a green. Like when you're looking at cosine, there's infinite many answers, right? There's infinite many answers when x equals 1/2. But there's only one answer within that restricted domain that meets it. That's why that works, okay? That wasn't something actually I taught with my students. So that's actually something I'm going to bring up next. That's something I'm going to bring up for next chapter, but I figured it'd be a good time to bring it up for you guys. So for our last function, tangent here, what we have is tangent inverse of negative 1. Now again, a lot of students confuse this tangent negative 1 with the x and the y-axis. But remember, the points that lie on the x and the y-axis. But remember, tangent is the y-coordinate over the x-coordinate. So the only time, again, first of all, tangent is going to be negative is in the second and the fourth quadrant. And remember, tangent is only going to be 1 at the angles of, you can see square root of 2 over 2 over negative square root of 2 over 2, right? Those are the exact same. Even though they look crazy, they're fractions or radicals, but they're exactly the same. So when you take the y over the x, that's negative 1. Y over the x, that's negative 1. So remember, these have, those have the, I don't know what I was going to say. I'll just move on from there. So the problem with this, though, is remember tangent has the restriction. Maybe that's what I was thinking of. I don't know. So the restriction here is negative pi halves again to pi halves, just like sine. All right, but here's a problem. our two angles, 3 pi over 4 and 7 pi over 4, do not fall within the restriction, right? It goes outside of that restriction and then comes back in, or at least 3 pi over 4 doesn't even land on it. So we know if it's going to satisfy, it has to be in this first and fourth quadrant. Now 7 pi over 4 looks good because it at least has the terminal side within the fourth quadrant. The only problem is the angle 7 pi over 4 is larger than pi halves, right? Pi halves is only from here to here. So 7 pi over 4 does not meet that restriction. However, if you do the negative version of that, right? So if you look at these, you say, oh, why don't I go from here to here? Well, you can do that, right? You can still get to that terminal side using the negative angle. That's a coterminal angle. So now I just got to figure out, well, how far is this to here? Well, again, 3 pi over 4 and 7 pi over 4 have the same reference angle. That reference angle is pi over 4. So they're both pi over 4 away from the x-axis. Because again, remember, pi over 4 over here is positive square root of 2 over 2, comma square root of 2 over 2. So therefore, the answer is just going to be negative pi over 4. And that gives you this coordinate point, which satisfies, gives us -1, and that also satisfies our restriction. All right, so now let's get into some more examples. So again, with my students, I'm hoping that you're at the same point that I'm expecting my students to be at, where you kind of understand a lot of the points on the unit circle. So therefore, I'm not going to go in depth as far as explaining how and where these points came to. If you're a little weak on the unit circle, I would recommend having that in front of you. So therefore, as I am saying, where these points and angles are coming from, you can quickly kind of check my work. So sine of negative pi square root of 2 over 2. So what I'm going to do is I'm just going to kind of do a rough little sketch here. Sine is negative square root of 2 over 2. That's going to either be down here or down there. And again, you can't use these two angles, right? Those two angles are not going to work. It has to be this angle. So now I just need to figure out, well, what is basically that angle? How, what angle gives me a y coordinate of negative square root of 3 over 2? What is that reference angle going to be? And the reference angle in this case is going to be pi over 3. So the answer here is a negative pi over 3. Because the sine of pi over 3 would give you a positive square root of 3 over 2. So if it's negative, it's going to be in the fourth quadrant, which gives me a y coordinate negative. Cosine inverse of -1. Well, remember that's when the x coordinate is -1. Well, that's going to be this point over here. Remember, cosine has to be between 0 and pi. So obviously, I want to make sure I'm going in the positive direction. It does include 0 and pi, that restriction. So therefore, my answer here is just going to be pi. Again, we're looking for the angles, right? For C is I'm looking for when is tangent equal to square root of 3. So when tangent's equal to 1, like that's easy. It's square root of 2 over 2. So now I just got to figure out, well, when is it going to be square root of 3 over 2? So we only have two other options. We have, we have 1/2 over square root of 3 over 2. Or we're going to have square root of 3 over 2 divided by 1/2, right? Those are your other coordinate points from the unit circle. Y over x, or you could have this be y over x. Well, hopefully you've done a lot of work so far with these, and you recognize that this is going to be your coordinate point. So now we just need to be able to determine, what coordinate point is that when x is 1/2 and y is square root of 3 over 2. Well, that's going to be pi over 3. Now again, since this is positive here, that's pi over 3. That's going to give you your coordinate point that we were looking for, this 1/2, comma, square root of 3 over 2. So at this point, let me just write this out there anyways. That's a positive 1/2, negative square root of 3 over 2. Let me draw these points in so you can see. So therefore, you can see that's the y coordinate over the x coordinate, which gives me square root of 3. It's in the first quadrant. So that one's rather nice. Sine inverse of 1. So again, that's when what angle makes the y coordinate 1? Well, that's going to be up here. Remember, it has to be between negative pi halves and pi halves. So that's 0, 1. So you can see that angle is pi halves. And then we have when is cosine going to be negative square root of 2 over 2? Well, again, understanding this cosine has to fall within these restrictions from 0 to pi. Well, cosine's only negative here in this second as well as the third quadrant. So, what are these two angles? Well, it's not going to be this angle. I mean, I could figure it out if I wanted to, but I just know it has to be this one. So what is that angle? What is the angle when the cosine is going to be a negative square root of 2 over 2? And when you look at the unit circle, you can see that that angle is going to be 3 pi over 4. So one thing actually I didn't mention in my notes, that's kind of a little tip that actually I gave away to my students up here, is notice that none of the angles that we chose, or look at least the restrictions, nothing is in the third quadrant, right? So when you're determining, what angle makes sense, if you have an angle that's in the third quadrant, that is not going to be the answer. So the third quadrant does not meet either of our restrictions for sine, cosine, or tangent. So therefore, if you immediately are trying to choose between an angle between the third quadrant and something else, you don't need to think about the angle in the third quadrant. That is definitely, that doesn't match any restrictions. All right, last one is when tangent is equal to 0. Now again, remember, tangent is y over x. So for this one, we need to look at, what are the coordinate points between negative pi halves and pi halves, where the y coordinate over the x coordinate is going to be 0. Okay, so you can see 1 over 0, that's undefined. Negative 1 over 0, undefined. The only point that works is 0 over 1. You can see that's undefined. So therefore, that angle, which is basically not moving anywhere, is just going to be 0. So that's kind of the basic idea. Again, this really depends on your being comfortable with the unit circle. And, I told my students, right now, you can rely on the unit circle, but eventually we need to get to the point where, you are able to not have to sketch this graph every time or look at the unit circle to try to determine what the coordinate points are. Because we start picking things up. You can see now we're going to do some composition. So if you remember, composition is plugging one function into another. And here, basically all we're doing is we're composing trig functions with their inverse, or inverse trig functions with another trig function. The basic idea here is just to really do the inside first and then work your way outside. So in this case, you can see I kind of did two problems here. I did the first problem, which is on the inside, sine of pi over 6. So I graph pi over 6, I say sine is equal to 1/2. So now this is equal to 1/2. So therefore I just rewrite the problem, cosine inverse of 1/2. So again, that's looking for what is the angle? What is the angle that produces 1/2 that meets the restriction of cosine? The only angle that is positive 1/2 that meets the restriction is going to be pi over 3. And remember, when you're, when you're looking at these, it's either a first or second quadrant for cosine, right? If it's in the first quadrant, it's positive. If it was negative, it would be in the second quadrant, right? But those are kind of two options. You can kind of see how that kind of works. For sine, it's kind of the same thing. If it's positive, it has to be in the first quadrant. If it's going to be negative, it's going to be that same acute angle, but just in the fourth quadrant. So anyways, let's do this again. Sine of 5 pi over 4, well, that's going to be the y coordinate, which is y coordinate negative square root of 2. Sine inverse of negative square root of 2, you can't use that angle, so you're going to use the angle that's in the fourth quadrant, the negative version of it, which is negative pi over 4. And you can see negative pi over 4 gives you that y coordinate of negative square root of 2 over 2. Last but not least here, we have negative 1/2, our cosine inverse of negative 1/2. So now we're actually doing the inverse first. So the cosine inverse of negative 1/2 is going to be 2 pi over 3, because we know if it's cosine's negative, or cosine, if you're doing the cosine inverse of a negative answer, or of a negative ratio, that angle is going to be in the second quadrant. And then we just do the tangent of 2 pi over 3, which is square root of 3 over 2 over negative 1/2, which we already kind of talked about. But again, you're doing an angle that's in the second quadrant, so we know it's going to be a negative square root of 3. All right, so now let's go and work on some more composition problems. Looking fun. All right, so in this one we have cosine of pi over 3. So again, I'm just going to kind of work through this, step by step, or just one by one. I'm not going to, or maybe I'll show the graph maybe of the first angle. Actually, I'll do the graph of the second one. Whatever the inverse is, I'll do that. So we have cosine of pi over 3. So cosine of pi over 3, that's going to equal pi over 3, cosine of pi over 3, that's going to equal 1/2. And the sine inverse of 1/2, again, to meet that restriction, is going to be right here, which is positive 1/2, comma, square root of 3 over 2. And so that angle, hopefully you got, is going to be pi over 6. For next one, sine of negative 2 pi over 3. So negative 2 pi over 3, this one we probably need to do 2 here. So negative 2 pi over 3 is right here. So that y coordinate of negative 2 pi over 3 is going to be a negative, let's see, that coordinate point is negative 1/2, comma, negative square root of 3 over 2. So now that's going to give us a cosine inverse of negative square root of 3 over 2. Now to evaluate the negative square root of 3 over 2, again, it's going to be a negative version. So therefore, that's going to be in the second quadrant. And negative square root of 3 over 2 is going to be when cosine, right? That's negative over there. So therefore, that coordinate point in the second quadrant is going to give you a 5 pi over 6, because that coordinate point is negative square root of 3 over 2, comma 1/2. So that angle is going to be a 5 pi over 6. All right, well, I guess I'll just work my way down. I'm not sure, A, B, C, D, whatever. So sine inverse of 1, we kind of did that. Remember, that was pi halves. So that's that point right there, which is 0, comma 1. So therefore, this is equal to the tangent of pi halves. Oh, I'm sorry, yeah, sine inverse, right, is just going to equal pi halves. Now the tangent of pi halves, we already have the coordinate point here. That's y over x. Well, that's undefined. All right, let's go ahead and work on this one. So tangent of 3 pi over 4. So if we were to go to 3 pi over 4, that's in the second quadrant. Right, remember that's going to be a negative square root of 2 over 2, comma square root of 2 over 2. So that's going to equal negative 1. So we have sine inverse of negative 1. Well, when is the y coordinate going to be negative 1? What angle? Again, has to meet this restriction. And that's going to be the coordinate point 0, comma negative 1. So that's going to be angle negative pi halves. Let's look at cosine of negative pi over 3. So negative cosine of negative pi over 3 is going to be down here. Negative pi over 3 is going to equal 1/2, right? Because that coordinate point is positive 1/2, comma square root of 3 over 2. So now that's going to be the cosine inverse of 1/2. And when is cosine equal to a positive 1/2? Now again, it can't be this angle because again, remember cosine has to be in the first and the second quadrant. So since cosine has to be positive, we know it's going to be in the first quadrant. And you can see that angle is going to be this angle right here, 1/2, comma square root of 3 over 2. And that's going to equal pi over 3. All right, last one here. Tangent inverse of negative square root of 3 over 3. And a lot of people look at this and be like, no, not going to do this one. But again, like, think about this, guys. And again, this is where like the practice comes in. You already have square root of 3 over 2 over negative 1/2. Like when you have square root of 3 over 2 divided by 1/2, we know that's going to give us square root of 3. Our only other option here is going to be 1/2 divided by square root of 3 over 2. Like that's the only other way based on the unit circle for the points that we have on the unit circle that's going to give us that. And again, when we simplify this, that's exactly what happens. When you multiply by 2 on the top and the bottom, for those students that didn't do their work, you get 1 over square root of 3. And when you rationalize the denominator, you get square root of 3 over 3. So you can see how that works. Now, again, that's the, let's just make this negative. There you go. Okay. But again, this tells us, now again, we don't know where the x and the y is. We actually don't know where the negative is, but we know that's the y and that's the x coordinates, right? So what coordinate point then is going to be giving us this, cosine inverse or tangent of y over x? When that is the y coordinate, that's the x coordinate. So if we look at this, well, we know tangent is going to be negative. Tangent inverse has to be negative down here, right? It has to be that negative version. And we say, well, it's actually not going to be y. It's going to be the, y works. So this would be x coordinate, square root of 3 over 2, comma, negative 1/2. So for what angles now, what angle gives us this negative version, right? Because you can't do the regular version. You have to stay within that fourth quadrant. So that angle is going to be a negative pi over 6. So now you're just going to do the cosine of a negative pi over 6. Well, if you look at that cosine negative pi over 6, you can see that the cosine is just going to be the x coordinate, which is going to be a square root of 3 over 2. Okay, so there you go, ladies and gentlemen. And again, you can see, one last thing I want you to remember is, again, when we're looking for the sine inverse, right, we're finding these angles. When our last operation is actually taking the tangent or the cosine, we're actually getting a value, right, that ratio. So again, that's that difference between evaluating trigonometric functions and evaluating the inverse trigonometric functions. All right, on to the next one, which is evaluating with triangles. So everything that we did up up here. I didn't really kind of explain why we're using the unit circle, but we were using the unit circle because these were all angles or values that we are familiar with from the unit circle, like pi over 3, 3 pi over 4, negative pi over 3, negative 2 pi over 3. Like those are angles that we recognize from the unit circle. 1 and square root of 3 over 3, or negative 1/2. Like those are points, or at least ratios, that we recognize from the unit circle. So when you see that, use the unit circle. But again, don't forget, the unit circle is just a easy way for us to take triangles and like organize that information, right? Because that's all the unit circle is. It's just made up of special right triangles on a coordinate grid. So the unit circle is still us evaluating the sine, cosine, tangent of special right triangles. It's just we simplified everything and put them on a circle, basically. So the reason why I bring that up is because a lot of students, they get used to using the unit circle, and then I provide them something like this, and they're like, crap, what do I do? Well, again, you're going back to our basics. Like, remember, cosine, yes, it's the x-coordinate, but it's the x-coordinate of a point on the unit circle. If that point is not on the unit circle, it's not the x-coordinate. It's x over r, where r represents the distance away from the origin. Or if we have a triangle, r would represent the hypotenuse, and x would represent the adjacent side. So again, remember, cosine is also adjacent over hypotenuse. So they're just different definitions based on the information. So in this case, we have cosine inverse of 4 over 7. So the cosine of something equals 4 over 7. I don't know what that angle is, so I'm going to call it theta. Now, this is very important to understand. So if I say the cosine inverse of 4 over 7, I don't know the answer. I don't know the cosine of what angle gives me 4 over 7. But again, there's a couple important points. One, I know that is not an x-coordinate that's on the unit circle. And two, I don't know what the answer is, so I'm just going to use a variable theta. So therefore, I'll say, all right, this is going to equal theta, right? So I basically just said, I don't know what that answer is, but I'm just going to call it theta. So now I need to figure out what is the tangent of theta. So here's the nice part. If I have cosine inverse of 4 over 7, this goes back to our first lesson. This is enough information to draw a triangle. Cosine of theta equals 4 over 7. That is your adjacent over your hypotenuse, right? It's not on the unit circle, so it's not the x-coordinate. It's not on a coordinate grid, so it's not x over r. It's the adjacent over hypotenuse, so draw a triangle. So I put the 90 degree here, put the theta here, and I say that's my adjacent, that's my hypotenuse. Do the Pythagorean theorem. This is a triangle in space, so we don't need to do plus or minus. And you can see the opposite side is square root of 33. So now doing the tangent is square root of 33 over 4. And there you go. You are done. The next one, again, looks completely confusing, right? But again, remember, like, sine inverse of this ratio, which of course, I don't even know what the value of x is. So of course, I don't even know if it's on the unit circle. This ratio is equal to some angle. What is that angle? I don't know. So let's give it a variable, alpha. So therefore, if this is going to be called alpha, then let's just put alpha there. So what is the cosine of alpha? That is really our question. So again, going back to that statement that I talked about at the beginning, if this is equal to alpha, then the sine of alpha equals 2 over, this. Again, this is not a coordinate point on the unit circle. At least we don't know it is. So we're not going to say that's the y-coordinate. We don't know it as far as on a coordinate grid, so we're not going to do y over r. But again, if you think about this as a triangle, you could say, oh, that's opposite over hypotenuse. So if I put opposite over hypotenuse as base alpha there of a unit circle, I can now solve for my alpha. So by using the Pythagorean theorem here, so I have quantity x, square root x squared, or square root quantity of x squared plus 4. Well, when I go and square that, I just get x squared plus 4. When I solve for x, or a, I just get x. So, oh, that wasn't a. Yeah, I guess so my a is equal to x. So now I'm just trying to figure out what the cosine is, which is x over square root of x squared plus 4. And then if you rationalize the denominator, basically multiply by the square root of x squared plus 4 on the top and bottom, you get x times x squared plus 4 over x squared plus 4. So the only way to get around this, guys, is just to practice. So let's go and do this. But hopefully you guys recognize, like, it becomes fairly basic. Like, I'm not going to rewrite these equations anymore, but hopefully you recognize, like, this is opposite over adjacent. So for some angle, now let's call this angle theta. So if this is theta, this is opposite over adjacent. So really, I'm just going to do what is the sine of theta. So let's do the Pythagorean. Let's call this c. So 2 squared plus 4 squared. So that's going to be, so I'll do c squared equals 2 squared plus 3 squared. We've already done this plenty of times. So that's going to be the square root of 13. So the sine is going to be opposite 3 over the square root of 13. And therefore, we'd say the sine of theta equals 3 square root of 13 over 13 when you rationalize the denominator, which at least in my class, I made sure the students always simplify their solutions with that. Let's go and work on this one. This one has a reciprocal function, but that's cool. Like again, what is a reciprocal? Oh yeah, that's hypotenuse over opposite, right? You could write the equation again if you wanted to. Let's call this angle, I call this one theta. Let's call this one alpha. So again, let's draw another triangle. I like to just draw all my triangles the same. So therefore, this is 13 over opposite. Now, hopefully you recognize this is a Pythagorean triple. So you could do the Pythagorean theorem, but hopefully you recognize that answer is 12 because 13 squared plus 12 squared, 13 squared equals 12 squared plus 5 squared, okay? So now we just need to figure out the secant, which is going to be a hypotenuse. So therefore, we're having secant of alpha. Well, again, alpha here, so that secant is hypotenuse over adjacent. So that's going to be 13 over 12. All right, so now we have the ones with the variables. But again, guys, the same really idea is going on here. Cosine is going to be adjacent over hypotenuse. And let's call this angle beta. So let's draw a nice little triangle. Okay, so we have adjacent over hypotenuse. Let's call this adjacent side here A. So I can say a squared plus 1 squared equals x squared. When I solve for a, I'm going to get x squared, square root of x squared minus 1. So I'm kind of skipping some steps here because we've already kind of done this a lot. And again, we don't need to do plus or minus again because this is just a triangle in space. So therefore, that's a equals x squared minus 1. So now we're doing the sine. Wait a minute. Oh, I wrote that wrong. I was wondering. I'm like, there you go. Thankfully, nothing got messed up. That's the adjacent over hypotenuse. Okay, so therefore, a is x squared minus 1. So now when I want to do the sine, it's going to be, so let's call this beta. So therefore, the sine of beta is going to equal the square root of x squared minus 1 all over x. Right, so I'm equaling to beta there. But again, you don't really need to. You could just write the answer here up there as x squared minus 1. You know, if you are going to be introducing a new variable, make sure you have that defined from there. So for instance, we would actually really need to do this like 1 over x equals beta. Okay, for the last one here, I have x over 2. So again, same kind of thing. Let's call that for a triangle. Let's just go back to theta. So cotangent, remember, is adjacent over opposite. So we have x over 2. Again, using Pythagorean theorem, let's call this c. C squared equals x squared plus 2 squared. So therefore, c is going to equal x squared plus 4. And again, we're trying to find the sine here. So the sine of theta. Stop. Or let's just set that equal to. So the sine of this theta is going to be 2 over that. So that'd be 2 over square root of x squared plus 4. And then you rationalize the denominator. And there you go. That is our answer all nice and scrunched in there. So just remember to rationalize that denominator, at least for the simplified form. So that was it basically with triangles. So we have, you know, when we're using the unit circle and we have triangles, there's one less problem oh, the reciprocal. Oh, I did do that problem. Oh, okay. All right, so I'm sorry, I made a mistake. So we're going to do So sine inverse of pi over 4. So I'm actually going to erase this. Let's use that one. Oh, crap. So why don't I do, yeah, okay, let's do sine. That's fine. So we have sine inverse of sine pi over 9. Okay, that worked. Oh, I already did the answer. Oh, cool. All right. So last one, I took off the reciprocal. I'm not going to deal with that for this chapter because we're gonna work on that actually next chapter. We'll talk about that. So for in this example, what I want to do is, again, understand the 5 pi over 7. So, or what about if we do 5 pi over 7? Well, that's not an angle that we're used to. We don't know the point for 5 pi over 7 on the unit circle. And we can't draw a triangle, right? Because when we drew a triangle here, for these values, we drew triangle because we were given the inverse, right? So we could create, those were the sides of the triangle. Here, we're given the angle. So we don't know the sides of the triangle. But we also don't know the point on the unit circle. So the way I explained this problem to my students was, I said, why don't we do something that's very, very similar? Why don't we do tan inverse of tangent of 5 pi over 6? So when we're doing tangent of 5 pi over 6, all right, we know that's in the second quadrant. We know whatever this point is. Now, again, you don't really need to know the point. In reality, whatever this point is, we do, hopefully you know the point is negative square root of 3 over 2 comma 1/2. But notice I didn't write it down because we know that's not the answer, right? When I'm trying to find the tangent inverse of that angle, which is 5 pi over 6, I can't use that angle, right? Because the angle has to remain within this quadrant. So it can't be this angle. And so it has to be this negative version. Well, again, how do we figure out that angle? Well, if this angle is 5 pi over 6, that means it has a reference angle of pi over 6. This angle down here is going to produce the exact same tangent, y over x, that's going to be negative, right? Because it's either in the second quadrant or the fourth quadrant. So these reference angles are exactly the same. I use this angle to find this reference angle, which is pi over 6. So therefore, I know this angle has to be the negative version, right? Because you can't go outside and come back in. So therefore, you're going to use, so this answer would be negative pi over 6. So I use that understanding to explain this one. If I have 5 pi over 7, that's again going to be in the second quadrant, right? Because all the way halfway around is 7 pi over 7. Halfway around would be 3.5 pi over 7, right? So it's going to be in the second quadrant. So therefore, tangent's negative. The only other angle that's going to give me a negative tangent is going to be an angle in the fourth quadrant. But I can't go, remember, I still have to remain between negative pi halves and pi halves. So I can't go past pi halves. I have to use the negative version. So I have to go from here to here. Well, remember, these are the same reference angle. So if this angle is 5 pi over 7, how far is it from here to here? And that answer is 2 pi over 7, right? 5 pi over 7 plus 2 pi over 7 gives you 7 pi over 7, which is pi. So this reference angle is going to be 2 pi over 7. We need to go in the negative direction, which is a negative 2 pi over 7. All right, so I'll have to fix up these slides, and I apologize for looking at that. So let's go and take a look then at our angle. So actually, I already did this one. I didn't mean to do this, but let's just go and work through it again. I'll work through it from step by step. So, well, again, you have your angle, sine of pi over 9. I don't know where pi over 9 is, like where exactly it is, but I know it's in the first quadrant. It's going to be somewhere right there. I have no idea what that coordinate point is on the unit circle, but again, I don't need to. So if here's my angle, let's just pretend, whatever, like you can see up here, I just said exclamation mark, or not question mark, like what is it? But it doesn't matter. All I know is if I need to find, this y coordinate, let's just call this y coordinate A. So what is the sine inverse of A, right? That's going to equal the sine inverse of A. Well, again, we need positive A. Sine is only going to match the restriction here in the first quadrant, which is then just going to give us pi over 9. Okay, so again, the y coordinate, remember, represents that A. Sine inverse of A is just going to be pi over 9. So the nice thing is when you have angles that's in the first quadrant, the sine and the sine inverse actually undo each other, right? The typical inverse operations, they undo each other within the same restriction. So you don't have to worry about the restrictions. However, once you get outside that first quadrant, it matters. So again, we don't want to just say, oh, the answer is negative pi over 5. No, it doesn't work like that. Because let's look at this one. When I do a negative pi over 5, that's down here. So, let's call this answer A here. Well, what's important about A? Is A positive or is it negative? Well, A is positive, right? So then you say, well, this angle, though, doesn't match my restriction. So my angle then has to be up here, right? Because I still need to get a positive A, but I have to match the restriction. So instead of doing negative pi over 5, I need to do the positive pi over 5. Okay, let's do another one with sine. So this one is going to be at negative 8 pi over 9. So let's go ahead and graph where that would be. Again, we know that 9 pi over 9 would be halfway around a circle, right? So negative 8 pi over 9 is just going to be just short, right? And that's going to give us a reference angle here of pi over 9. Now again, remember reference angles are always positive, right? So that's going to be our reference angle, pi over 9. So that's negative 8 pi over 9. Okay, so the important thing though is when we look at this coordinate point, we have no idea what the coordinate point is on the unit circle. All I know is that y coordinate is going to be a negative answer, right? So the only way that I can figure out that negative answer that's going to match my restriction is to go over here. This angle also produces a negative A. So then what is that angle? Well, that angle is going to be the reference angle, but in the negative direction. So that'd be a negative pi over 9. And last but not least here, we have 6 pi over 5. So again, that's going to be another one in the third quadrant here. So let's go ahead and graph that. So again, 5 pi over 5 is halfway around a circle. So 6 pi over 5 is going to be right there. Again, we recognize the reference angle is going to be a pi over 5. And okay, so whatever this point is on the unit circle, whatever it is, we know cosine in this case is going to be negative, right? Because you're in the third quadrant. So, so let's just call this a negative A. Whatever, we don't even know what A is, or we don't know what the y coordinate is, but it doesn't matter. We know we have to match the restriction. We have to find our other angle, which is going to be right here. So we know that has the same reference angle, pi over 5, right? This one's pi over 5 larger than 5 pi over 5, but we need to get to one that's going to be pi over 5 shorter, right? Because again, this is going to give us that same angle, but this angle at least is going to fall within the restrictions of cosine. And therefore, this angle is going to be a 4 pi over 5. Right? Because these two angles are going to have the same reference angle. The difference is this angle matches the restriction where this angle is outside of the restriction. So there you go, ladies and gentlemen. That is it for inverse trigonometric functions. I hope this helped because we dealt with angles, evaluating the inverse for angles that we didn't know their points on the unit circle, but without using a calculator. We were able to use the composition using right triangles, again, without using a calculator. We were able to use the unit circle to evaluate our composition, as well as to just evaluate the inverse of trigonometric functions, again without a unit circle. Without a calculator. So you can see using that unit circle is so powerful and so helpful. So I hope this helped you out as far as learning inverse trigonometric functions. Obviously, this is something we're going to be building on. So I did purposely leave some of the some definitions and things out. So therefore, I wanted students to get this foundation set before we move on. But this is the end of the chapter, and I hope so far that has helped, and we'll look forward to seeing you on to the next one. Cheers.